All right, let's talk about one of the most famously tricky concepts in all of programming: monads. You've probably heard the term whispered in hushed tones, and if you've ever felt a little intimidated by it, you're definitely not alone. But today, we're going to pull back the curtain. We're going to see that monads aren't some scary abstract monster. They're actually an incredibly smart solution to a problem we run into all the time. Okay, let's get into it. It all really boils down to this one simple question. As a programmer, you're constantly making this choice, whether you realize it or not. Are you going to write pure code, the clean, predictable, easy to understand stuff? Or do you need to embrace impure code to handle all the messy real-world things like errors or state or network requests? This is the fundamental trade-off. And here's that trade-off in a nutshell. On one side, you've got pure functions. They're a programmer's dream, really. You give them an input, you get an output every single time. It's clean, it's testable, it's simple. But the real world is messy. We need to deal with stuff that isn't so predictable, what we call side effects. That's where impure code comes in. It gives us all the power we need, but we lose some of that beautiful simplicity along the way. So the big question is, can we have our cake and eat it too? To really understand why we need a special trick for this, we're going to take a really simple, pure program and just see what happens. We'll watch as we try to add these necessary impure features, and you'll see how the core idea of our code gets totally buried under a bunch of extra stuff we're going to call plumbing. Okay, so here's our starting point. It's about as pure and simple as it gets. This function just evaluates a division problem. It takes the left side, evaluates it, takes the right side, evaluates it, and then divides the two. It's crystal clear, right? Super easy to understand. But it's also pretty fragile. Right. What happens if part of that expression is a division by 0? Well, our perfect little function just crashes. That's not great. So, first challenge. Let's make it safer. Let's add some proper error handling and hopefully not destroy its simple elegance in the process. And yikes, look what happens. Our nice one-line function just exploded into this mess of boilerplate. The actual division we care about is still in there somewhere, but it's totally buried inside all of these checks to see if an error happened at any point. This is the plumbing. It's all the extra code we have to write just to manage the possibility of an error. Okay. Let's hit reset for a second. Forget about errors. Let's try a different challenge. What if we just want to count how many division operations our function is doing? This means we have to manage some kind of state. In this case, a simple counter that changes as the program runs. And would you look at that, our simple code gets messy all over again, but in a totally different way. Now, to keep track of the count, we have to manually pass this counter into every function call, get a new count back out, and then remember to pass that new count into the next call. It's tedious, it's error-prone, and the plumbing is just getting worse. All right, one last try. What if we want to produce some output? Let's say a log or a trace that shows every calculation step as it happens. How hard could that be? It's a total disaster. I mean, seriously, can you even find the original logic in there anymore? Our simple, beautiful idea of dividing one thing by another is completely lost in a sea of string manipulation and passing logs around. No matter what we tried to do, handle errors, manage state, create output, we ended up drowning our logic in all of this tedious, repetitive plumbing. There has to be a better way. And of course, there is. The big aha moment comes when we just step back from all this messy code. Let's start focusing on the specific details of what we were doing, errors, state, output, and instead look at the how. How was our code forced to change in each of those 3 ugly examples? Because it turns out there's a hidden pattern. In every single one of our messy solutions, we actually ended up doing the exact same 3 things. First, we stopped working with plain values and instead wrapped them in some kind of container or context. Let's just call it type M for now. Second, we needed a way to take a normal plain value and put it into that wrapper. We'll call that function unit. And third, we needed a special way to chain our operations together, a function that knew how to handle our wrapped value. And that, right there, is a monad. That's it. It's not some mystical thing built into a language. It's just a design pattern, a recipe for sequencing operations that have some extra context. It's just these 3 parts: a wrapper type, a function to put things in the wrapper, and a function to chain wrapped things together. That's the whole secret. So, what's the big payoff? Why go to all this trouble to spot this pattern? Well, the payoff is that once we've identified the pattern, we can create an abstraction for it. And we can use that abstraction to make our code clean again. So let's rewrite our evaluator one last time. But now we'll use our new monad pattern. Just look at that. It's almost as clean and simple as the very first version we wrote. The logic is totally clear again. Evaluate T, then evaluate U, then divide the results. All of that horrible, messy plumbing for handling errors or state is now completely hidden away inside that little question mark operator, which takes care of all the sequencing details for us.
And now, here's the real magic. This is the crucial part. We never have to change our clean eval function again. We can get all those different behaviors we wanted, exceptions, state, logging, just by plugging in different definitions for our monad. You want error handling? You just plug in a monad whose bind operator knows how to stop if an error happens. You want to track state? You plug in a monad that knows how to pass the state along. It's like having plug-and-play behaviors for your code.
Now, you might be thinking, okay, that's a neat trick for a toy example, but this pattern for taming complexity is absolutely everywhere in modern programming. Once you know what you're looking for, you start seeing it all over the place. This pattern is the secret sauce behind a ton of powerful tools. It's used to manage state cleanly, to build powerful parsers, and to handle complex things like non-determinism. But here's the big one. If you have ever used promises or async await in JavaScript or C#, guess what? You've been using monads the whole time. That .then method on a promise, that's just another name for our bind operator, chaining asynchronous computations together. So the next time you find yourself writing a bunch of repetitive, boilerplate code to manage errors or state or asynchronous calls, just stop for a second. Ask yourself if you're just reinventing this pattern from scratch. Because the monad isn't something to be afraid of. It's a tool, a powerful tool for hiding all that plumbing and letting the simple, elegant logic of your program shine through again.